isotopes. All atoms of a given element must have the same number of protons. That's not true for anything else. It's only true for protons. So it turns out that the number of neutrons and electrons can vary. Isotopes are basically, you're comparing different atoms that have different number of neutrons. So they have the same Z value, the atomic number, meaning they have a different number of N possible for an isotope. Thus, that means they have a different mass. So their masses end up being different. Alright, so let's go ahead and take a look at the different particles and their relative masses. Since these particles are extremely small, we have to use different units. Using units like kilograms or grams does not make too much sense, because if we're on the order of kilogram, look how small this has to be. These numbers are times 10 to the minus 27. That means there are many, many zeros before that number, meaning it's a very, very small mass that we're going to write down here. The other unit we like to use is the AMU, and that stands for atomic mass unit. Atomic mass unit. And once again, the reason why we want to use these units like that is for something very, very small. So we have the three different particle types: the proton, the neutron, and the electron. It turns out that the bulk of the mass is going to come from the protons and neutrons, and very little is going to come from the electrons. So these are not numbers that I would expect you guys to memorize. I'm just going to go ahead and write them out here. So it turns out that these are 1.67262 times 10 to the minus 27 kilograms. So it's a very small number. And notice here that the neutrons are about the same weight. Just a little bit heavier, but they're still extremely small. But then if you compare it to the electron, how many orders of magnitude are they different by? So this goes to 4 decimal places, so it's about the 4 decimal places, right? So what that is saying is it's approximately 10,000 electrons to equal the weight of one proton. So we basically say that they are massless, or the mass is negligible. Oftentimes you may hear people say that they are massless. They're technically not massless, but they're so light that they don't contribute much to the overall weight. Alright, and we have these AMU units. It works out where the mass in AMU for both the proton and the neutron are about 1. So approximately 1. Approximately 1. And then these are very, very small. And we say that's essentially 0. So in general, we say that in AMU, this is defined to be exactly 1/12 of a carbon-12 atom. All right, what the heck does that carbon-12 mean? So the general way that we write our formulas, if we're talking about isotopes, is we will have our element symbol. So here we have our chemical symbol. Up here we will have the letter A. That is our mass number. That is equal to the number of protons plus the number of neutrons. Remember, that's where all the weight comes from, right? So we're going to say that that is the overall mass. And then lastly here, on the bottom here, is the Z number. And recall that that is the atomic number. Oftentimes when you see these symbols, people will drop the Z off, because we can figure out what Z was just by looking at the symbol, right? So I know that carbon, the number on all the different versions of carbon are going to be a 6 here, so I don't typically write those. Alright, another way to express these are the element name. dash mass number. So that was the way that I did the carbon-12 up here. What I did, element name dash mass number. Let's take a look at the isotopes of carbon. And we can go ahead and make a little table here. All right, it turns out that there are three main forms of carbon. The most common one is carbon-12. And then it works out that carbon-13 and carbon-14 are significant enough that we can measure them. Percent natural abundance. What this number here on the end is how much each isotope naturally occurs. So as I mentioned here, carbon-12 is the most common. This is roughly 99.9%. So what that means that if you were to take a look at all the carbon atoms in your body, they are almost all in the form of carbon-12. Turns out that you have roughly 0.1% for carbon-13 and very, very little of the carbon-14. So it's less than 0.01% carbon-14. All right. How many protons does carbon-12 have? Or all of these for that matter. They all have 6, right? Because we're still calling it carbon, these are going to be the same. However, we have different isotopes here, so their mass number is different, meaning their number of neutrons is different. So carbon-12 has 6, and then what about carbon-13? 7, and then 8 for carbon-14. The first one is done for you. Recall that you go ahead and turn your percent abundances into a decimal by without a multiplication or division by 100. So division by 100. So your 99.984% becomes 0.99985. And it looks like here it was rounded to, I think it was rounded here. That's okay. And then same deal for the other ones. Notice here that this last one here, to make room, was already done for you, but this should have been a, with that 6 decimal places times 3. All right, so let's go ahead and take a look at this one here, lithium. So percent abundance, I'm going to go ahead and take a look at the first isotope. So that's 0.0742, and then multiply that by 6.015, and the units here are AMU. Okay, that is for lithium 6. The next one here, lithium 7, so 0.9258. Remember that these are unitless, your percent abundances. And then multiply that by your 7.016 AMU. Didn't leave myself enough room, but that's okay. 6.942. And the units are AMU. Alright, and am I going to be particular about sig figs on these? Nope, because everything here is table information. I usually take it to 4 or 5, just because. There's really no random reason why. Just take it to a couple sig figs and you're fine. Little bit of a history here I wanted to point out. Notice here how it's lithium 7. Lithium 7 is the most common isotope for lithium. And you guys may have heard of the soda 7-Up before. It turns out they actually used to put lithium into 7-Up. That's actually where the name came from. And it would make people feel up, it would wake you up a little bit. We now know that that's really bad to have that in commercial drinks. And then as you learn the history of sodas out there, you'll find that they used to put weird stuff in there. Like, you guys know where the name for Coke came from? They used to put cocaine in Coca-Cola. Yeah, that's where the name came from. So it literally was cocaine cola. But they no longer do that either, thankfully. But I just wanted to point out that you can use that to remember lithium. Lithium is 7, so that's 7-Up. That's where the name came from.